The 106,000 hours of preparation involve detailed planning, safety assessments, engineering designs, logistics, component assembly, and rigorous coordination efforts. The 72-hour blockade was a planned operation to minimize disruption to railway services. During this critical window, the team executed essential tasks, including the excavation of 7,500 tons of material, the positioning and assembly of massive bridge components, and the skidding of the entire bridge into place. Extensive coordination ensured that all resources, personnel, and equipment were in position to work around the clock. Despite adverse weather, including strong winds, the team successfully completed the installation within this tight time frame. During the 72-hour blockade, 7,500 tons of earth and materials were excavated to prepare the ground for the new bridge installation. This massive excavation was necessary to clear space for the foundations and support structures. Heavy machinery operated continuously, carefully removing and relocating soil while ensuring the stability of the adjacent railway line, allowing for precise bridge positioning. The two main steel beams, each weighing an impressive 107 tons, served as the primary structural elements of the new bridge. These massive beams were carefully lifted and positioned using specialized cranes, requiring meticulous alignment to ensure stability. Their installation demanded precise engineering and coordination, as they formed the backbone of the bridge, bearing its weight and enabling the safe passage of trains. The 43 meters of burning involved precise cutting and welding of steel components to shape and prepare the bridge structure. The bridge installation faced gusts up to 48.8 miles per hour, requiring careful handling, heightened safety measures, and constant adjustments to stabilize heavy components. The 86-meter skid track provided a guided path to slide the massive bridge structure smoothly into its final position with precision. To facilitate the bridge installation, around 100,000 tons of stone were used to construct temporary access platforms and robust foundations. These platforms created a stable and level working surface, essential for heavy machinery and safe personnel movement during the project. The stone foundations supported cranes, transporters, and other equipment while ensuring stability during the precise skidding of the bridge structure. This substantial amount of stone helped to distribute the load effectively, preventing ground settlement or instability under the immense weight of the steel beams and heavy equipment. The sill units, each weighing 50 tons, serve as the foundational supports for the bridge structure. These massive units were precisely positioned to evenly distribute the bridge's weight and provide stability during and after the skidding process. Made from reinforced concrete, the sill units are designed to bear substantial loads, ensuring the bridge remains securely anchored over the railway. The skid length of 20 meters facilitated the precise movement of the 604-ton bridge, ensuring accurate placement and alignment during installation. The skid duration of 109 minutes was a carefully timed operation that involved the precise movement of the bridge into position. Engineers and operators closely monitored the process, ensuring safety and alignment while managing the heavy load. This efficient timing was crucial for completing the installation within the tight 72-hour blockade. The 17.5 millimeters tolerance over a 45.5 meter length ensured precise alignment and stability of the bridge, crucial for safe rail operations. The bridge's construction involved the use of over 6,000 bolts to secure various components, ensuring structural integrity. With more than 1,300 individual parts, each required careful assembly and alignment. The bridge deck itself measured 40.5 meters in length, necessitating 3,300 counter-sunk holes to provide flush surfaces for a smooth finish, enhancing both safety and aesthetics. During the 72-hour blockade, a total of 3,660 work hours were logged by the project team, showcasing their dedication and commitment to completing the bridge installation on schedule. This intense period involved continuous, coordinated efforts from engineers, construction workers, and safety personnel, who operated in shifts to maximize productivity. Each hour was meticulously planned, with teams assigned specific tasks, such as excavation, steel beam installation, and quality checks. Safety was paramount, and regular briefings ensured that all personnel were aware of the risks associated with heavy lifting and adverse weather conditions. The extensive work hours reflected not only the technical challenges of installing a 604-ton bridge, but also the team's resilience and teamwork in achieving this critical infrastructure milestone. The use of 800 tons of new ballast was a vital aspect of the Lincoln Eastern Bypass Rail Bridge project, playing a crucial role in ensuring the bridge's stability and the overall integrity of the railway infrastructure. Ballast, typically composed of crushed stone, serves as a foundational support for railway tracks, providing stability and aiding in drainage. In this project, the new ballast was meticulously laid to create a solid base for the bridge and the surrounding track. Before the installation of the bridge, the existing ballast needed to be assessed and in some areas replaced to accommodate the new structure. This process involved removing the old ballast and carefully grading the subgrade to ensure proper drainage and support. The 800 tons of new ballast were strategically placed beneath the bridge and along the railway line, ensuring an even distribution of weight and helping to mitigate any potential settlement issues that could arise from the immense load of the bridge and passing trains. The completion of the Lincoln Eastern Bypass Rail Bridge is a significant engineering achievement that demanded immense planning, precision, and effort. This massive project involved the installation of a new bridge over an active railway line, requiring meticulous coordination and exceptional technical expertise. The project team faced various challenges, including time constraints, unpredictable weather conditions, and complex engineering requirements. However, the operation was successfully completed through a series of well-planned stages, each of which contributed to the overall success of the project. The completion of the Lincoln Eastern Bypass Rail Bridge is a testament to modern engineering capabilities and the dedication of the project team. Through planning, precision engineering, and exceptional teamwork, the team overcame a series of formidable challenges to deliver a vital piece of infrastructure. Cranes play a crucial role in construction, providing the necessary lifting power to transport heavy precast concrete components from ground level to their designated positions, ensuring precision and safety throughout the installation process. Each foundation component is installed with precise leveling to ensure that it sits exactly at the intended location. Advanced leveling tools, laser levels, and spirit levels are employed to achieve accuracy. This attention to detail is vital, as proper alignment ensures that the entire structure rests on a stable base, preventing All components are produced using high-strength materials and designed according to rigorous structural calculations, ensuring they meet specific load requirements and seismic standards for optimal safety and durability. Before shipment, entry points for underground facility piping are pre-drilled into each precast concrete component. This proactive approach streamlines the installation process at the construction site, minimizing delays and ensuring that utility connections can be efficiently integrated without the need for additional drilling or modifications during assembly. Foundation construction and backfilling are carried out simultaneously for high efficiency. The foundation components are specifically engineered with recesses and channels that facilitate high-strength mortar filling after the walls are erected. This design ensures a seamless connection between the foundation and the walls, enhancing the overall structural integrity of the building. The mortar fills any gaps, providing additional bonding strength and stability. By allowing for this filling after wall installation, construction teams can achieve precise alignment and leveling, ultimately reinforcing the entire structure against seismic forces and other potential stresses. The precise and strong foundation construction is completed in just one day. On the following day, the installation of precast concrete walls commences, marking a crucial phase in the construction process. Each wall panel is carefully positioned and lifted into place using cranes, ensuring precise alignment with the foundation. This approach guarantees structural stability and prepares the building for subsequent construction phases. The installation of precast concrete walls is a critical step in constructing a durable and resilient building. During this phase, careful attention is given to achieving precise vertical and horizontal leveling, which is essential for the overall structural integrity of the structure. First, each wall panel is carefully lifted into position using cranes, which provide the necessary lifting power and precision required for such heavy elements. Once the panels are in the air, crew members on the ground utilize advanced leveling instruments, such as laser levels and digital inclinometers, to ensure that the walls are perfectly vertical and aligned horizontally with the foundation. This step is crucial because even minor misalignments can lead to significant structural issues down the line, uneven weight distribution, or increased stress on the building materials. After lifting the wall into position, it is temporarily secured while adjustments are made to achieve the exact alignment. Construction teams pay meticulous attention to both the vertical and horizontal dimensions. Vertical leveling ensures that the wall stands upright, which is vital for maintaining the intended aesthetic and functional aspects of the structure. Horizontal leveling, on the other hand, guarantees that the wall aligns correctly with adjacent walls and structural components, contributing to the overall architectural design. Once the walls are correctly leveled, they are anchored to the foundation using high-strength bolts and other fastening systems. This anchoring process is integral to the stability of the building, as it prevents lateral movement during seismic events or high winds. The connection points are often designed with reinforced concrete elements to enhance durability and ensure they can withstand various forces. Additionally, as walls are installed, any necessary openings for doors, windows, or utilities are double-checked for accuracy. This attention to detail ensures that the final structure meets both design specifications and functional requirements. Proper wall installation sets the stage for the subsequent construction phases, ensuring that the building is not only aesthetically pleasing, but also structurally sound and resilient against external forces. Floor slab construction can utilize either precast concrete elements or cast-in-place methods, allowing flexibility based on project specifications and site conditions. Precast slabs are manufactured off-site for quick installation, while cast-in-place slabs provide customization and adaptability on-site. The choice between these methods depends on factors such as design complexity, budget, and timeline considerations. On the fourth day of the construction process, the focus shifts to the critical phase of constructing the roof structure. This step is essential as the roof plays a vital role in the overall stability and integrity of the building. The roof components, typically precast concrete panels, are transported to the site and prepared for installation. As the roof panels are lifted into place by cranes, a meticulous approach is taken to ensure that they are correctly aligned with the walls and the building's overall framework. During this installation, wall pins are inserted into pre-drilled fastening holes located in the roof components. These pins serve as essential connectors that help secure the roof panels to the walls, providing additional stability and preventing any lateral movement. The installation team employs precise leveling techniques to ensure that the roof components are installed correctly. This involves checking both the horizontal and vertical alignment of each panel to maintain the architectural integrity of the structure. Ensuring that each panel is level is crucial not only for aesthetic reasons, but also for the performance of the roof in various weather conditions, such as rain or snow accumulation. Once the roof panels are positioned and pinned in place, high-strength bolts are used to integrate the walls and the roof into a unified structure. This bolting process reinforces the connections, enhancing the overall strength and rigidity of the building. The use of high-strength materials ensures that the roof can withstand significant loads and forces, including wind uplift and seismic activity, thus contributing to the structure's durability. Additionally, careful attention is given to sealing any gaps between the roof and walls to prevent water intrusion, which is vital for maintaining the building's integrity over time. By the end of this day, the roof structure not only completes the external shell of the building, but also signifies a major milestone in the construction process, paving the way for the final interior finishing stages. The process begins with the preparation of HCP composite piles. These piles, typically 62.0 meters in length, are designed for strength and flexibility, making them ideal for various soil conditions. They consist of materials that provide superior resistance to environmental factors such as corrosion and degradation. Proper handling and storage of these piles are essential to maintain their integrity before installation. Once the piles are ready, the construction site is prepared for drilling. The first drill rig is utilized to create a borehole into the ground, reaching the desired depth for the pile installation. During this stage, lower casing installation is conducted simultaneously. Following the first drilling operation, a second drill rig is employed to continue the drilling and lower casing installation process. With the lower casing securely in place, the next step involves pulling the upper screw rod from the second drill rig. The upper screw rod serves to stabilize the casing during the installation of the pile. Similarly, the upper screw rod from the first drill rig is also removed. This action marks the transition to the next phase of the construction process, as both drill rigs now prepare for the installation of the composite piles. The installation of the HCP composite piles is a critical stage. The prepared piles are carefully lowered into the drilled and cased boreholes, ensuring they reach the intended depth. Proper installation is essential to achieve the required load-bearing capacity. After the piles are installed, the upper casing from the second drill rig is pulled out. This removal process is executed with precision to prevent any disturbance to the newly installed piles. The lower casing from the first drill rig is then removed. This step finalizes the pile installation, leaving the HCP piles firmly in place and ready for load application. Finally, a thorough inspection is conducted to confirm the final penetration amount of each pile. This verification ensures that the piles have reached the necessary depth and alignment, adhering to engineering specifications.